Welcome to ICDD's InSession webinars and Dr. Anja Dosen's presentation, Clay Analysis, Part 3. Please remember to visit ICDD.com for information on free webinars, educational events, PDF databases, and JADE software.
Welcome back to the Clay Analysis Part 3. So today I'm going to try and focus a little bit more on sample prep and sample analysis. So let's start with some general stuff, as we usually do, like some interesting things and some things that haven't really been said before. So how do clays form? So clays generally form by weathering of other minerals. They can form through hydrothermal alteration and diagenesis, or changes of primary minerals. So what is weathering? It's the breakdown of or dissolution of rocks and soils due to their exposure to the atmosphere. Clays form in many different environments, but they form, they're ubiquitous on Earth. They form in pretty much like in a lot of geologic environments. So one thing that we can sort of think of is that clays formed in similar environments are going to have some similar characteristics. So quick look at this, what we could call clay cycle, just showing different environments where clays form. So we can take a look at this as a volcano. Volcanoes will spew up clouds of ash. These clouds of ash can later turn into K-bentonites, a type of clay. Mud flows that are also produced by volcanic eruptions contain clay. Igneous intrusions can turn into clay by weathering. Minerals from igneous intrusions. Hydrothermal clay can form hydrothermally. During sedimentation, we have sedimentation of clay at a certain depth. Process of diagenesis is going to start becoming prominent, where one type of clay can transform into another. Then once we get to actual burial, like deeper depths or higher pressure, maybe from overburden pressure, we get to this low metamorphic zone, where again we have formation of different clays through diagenesis. And then if we get to higher grade metamorphism, we'll get formation of different phyllosilicates, like micas, like muscovite and biotite, for example. And then, as this gets uplifted, whatever has been buried and metamorphosed, and it gets uplifted, then weathering again takes control of these processes and starts forming clay. So that's sort of the cycle. And some like general characteristics of clay, things that we see. I'm gonna point out how much we see clay every day in life. So if we look at this here, this is just soil. Clay-rich soils, they look cracked and dry and let's say dead-ish during dry seasons. Once it rains, they will start changing. So you can actually witness these changes. You can just observe them happening, where clays hydrate and these cracks start to disappear. So the reason, I have this example, is this is something that if you're interested, you can take a look. There are a lot of examples online where you can see the videos of rehydration of clay that's used for pottery, because it's shipped as a dry brick, as this dry, slab of clay, and people will, artists, right, will just put that in a bucket of water. And depending on how malleable they want it, they will leave it for a different amount of time in water, so that they will let it rehydrate. So that is some of the very interesting properties in property that drives a lot of different processes. This possibility of rehydration and dehydration of clay. So clays, as we mentioned before, are naturally occurring phyllosilicates. They're sheet-like minerals. They contain very long sheets, elongated sheets along the basal plane, and the clay layers are stacked on top of each other. So clay minerals are very fine particle size of less than 2 microns. And here we can see clays, as I mentioned, can be expandable and non-expandable. And here we can see the difference in their interlayer spacing, or what we call despacing. For 1-to-1 clay, this, for example, is kaolinite. 1-to-1 is kaolinite. It's non-expandable clay, and then the interlayer spacing is more or less 7 angstrom. We'll talk about this more. And then we have 2-to-1 clays, tetrahedral, octahedral, tetrahedral clays. They're stacked in this fashion. This here represents the interlayer cations. And as you can see, then this interlayer is a little bit bigger, and it's about 10 angstroms. The example of this clay type is, for example, illite. And then we have here an expandable clay. So Montmorillonite clay is a very expandable clay, or clay that swells. Vermiculite is expandable as well. And what that involves is the possibility, like the ability of these layers to expand and contract when there is water or some polar organic molecule present. So these molecules will get in between the layers, and the layers will expand. Once it dries and the molecules are sort of squeezed out, the layers will contract. So this clay has a variable interlayer spacing. Okay, so clay layers are negatively charged. They have a net negative charge. As you can imagine, since being sheet silicates, they have a very high specific surface area, which allows for high cation exchange capacity. And that is, a cation exchange capacity is an important property of soils. And these are a lot of times dependent in a way on the amount and type of clay minerals. So cation exchange capacity represents how many cations a soil can hold on to. That is related to fertility of soils and nutrient circulation. So these cations are, as you can imagine, cations that plants need for growth and food. So calcium, magnesium, sodium, potassium, and so on. And the more nutrients, or the more these cations the soil can hold on to, the slower it can supply them to plants. So like slower meaning over time. And then different clay minerals have different cation exchange capacity, as you can imagine. Vermiculite has the highest and kaolinite has the lowest. And just to mention, organic matter that's always present in soil also has a high cation exchange capacity. So besides that, we have mechanical property of soil that also depend on the presence and the amount and type of clay minerals. So this is something where clay minerals are not as useful because we know the dry clay and wet clay behave differently. So there's something here that we call quick clays, and this is an example here. These quick clays can cause catastrophic landslides. They undergo very quick liquefaction, and the landslides happen in like seconds or minutes. As you can see, these cars are overturned because this happened like extremely quickly. Other than that, presence of more than 10% of soil clays that can swell in soil can cause structural damage to buildings. You can imagine, as they contract and expand, they can cause cracks in foundations of buildings. An interesting thing, clays have been linked to the origin of life, again, due to their sheet-like structure. They are thought to, may have been shielding the original or the, primordial molecules, shielding them from sunlight and helping due to the ability to concentrate organic chemicals, which we talked about, like, absorbing or including polar organic molecules in their interlayer spacing and their ability to serve as polymerization templates. So this is an interesting theory that I just wanted to point out. Clays and cultural heritage. I've seen that many of you are in cultural heritage, so I've included this slide to briefly go over some methods that are important in cultural heritage research and conservation. So as you all know, clays play a vital role in cultural heritage research, as they were used as building materials, as art materials for pottery and so on. So that's where methodologies like X-ray diffraction, spectroscopy, and chemical analysis play a role. They help determine the composition, some firing temperature for these materials, and sometimes the origin as well. So pigments and artwork, clays are often used in pigments, and they've studied to understand their composition and aging, because the aging of clays and their hydration and rehydration can influence the quality of art. And one of the things, again, where clay research plays a role is understanding the interaction of different parts of the atmospheric occurrences with clays, and it helps in developing strategies for the conservation, for cultural heritage conservation and art conservation. So having said all that, this was just a reminder, like how ubiquitous clays are and how widely used they are. So now we go back to challenges, because there's challenges never stop when it comes to clay. So we've talked about challenges, but we're going to talk about this again. Clays are notoriously difficult to analyze. They are very similar. They're never pure. So when we try to analyze clay, we want to make an effort to analyze pure, or like as pure of a sample as possible. So I'm going to talk about some purification methods for samples that contain various minerals. And I'm going to talk about sample preparation. And then one of the ways of obtaining pure clay sample is synthesis. So synthetic clays are a different story. And then, as we've mentioned before, X-ray diffraction is a major tool still in identification of clay minerals and clay types. And then sample preparation is a major step, if not the most important step, in clay analysis. Okay, we don't generally see a single phase clay mineral out in nature. They're going to be interstratified, or they're going to be a part of a sedimentary rock, or they're going to be contained in soil with many different minerals. So we want to separate these clay minerals from the bulk. And one thing that we always need to keep in mind is that that process is never 100% successful. So there are always going to be small amounts of quartz and feldspar present in the smallest fraction, the clay size fraction, which is less than 2 microns. I'm going to show again our PDF Fireflies database. And here I'm just going to mention that clay subfile contains not just clay subfiles. All PDF entries contain a comment section, but in the clay mineral subfile, the comments contain information about the impurity, the peaks that are visible in raw data, which helps immensely when you're doing your clay identification. So let's talk a little now about sample preparation. As we said, we want to work as pure samples as we can. So want to work with clays, we can start with removing something that some unwanted materials through physical or chemical treatments. So after we do that, we move on to size fractionation because we want to separate less than 2 micron fraction and work with that. So we want to remove the larger mineral grains, and working with less than 2 micron fraction provides more precise information about analyzing clay because it removes or tries to remove as many impurities as possible, and we work within the clay particle size range. So purification involves, as I said, removal of unwanted minerals. So we can just go over some here. These are the most common ones. So we can remove carbonates, for example, by using dilute hydrochloric acid, for example, or an acetate buffer. We need to pay attention to pH. All of these methods are published, so you can go to the literature and take a look. For removal of oxides and hydroxides, this generally relates to iron oxides. So we can try and remove the iron oxides by making complexes with citrates. And then if there's amorphous silica present, that can be dissolved in a boiling solution of sodium carbonate, and organic matter can be removed by using hydrogen peroxide, for example. All right, so let's say that we did that, and now we want to move on to size fractionation. So that involves separation of clay. So that is our goal will be to separate less than 2 micron fraction. And that way, as I mentioned, we are going to reduce the mineral, non-clay mineral contamination. We're going to reduce the presence of highly crystalline phases, and we're going to work within the clay particle size range. That is fractionation, is gravitational settling in a column of water that involves, so heavier particles are going to fall faster, and the clay fraction is going to stay in suspension. If we're working with a rock sample, we need to go through the procedure of separating clay from the rock. So these procedures will depend on the type of rock, and most will involve, crushing, shaking, sieving, and so on until we get to a certain particle size, and then all of these methodologies become sort of the same. So depending on your rock, you will need to go through a certain type of preparation. So once the clay is in dispersion, we don't want the clay minerals to flocculate, so we may use some anticoagulation agents to maintain the clay in suspension. So this is gravitational settling. So as you can see, all of these settling tubes contain contain different samples, clay-rich samples. Gravitational settling is following Stokes' law. It depends on the radius of the particle and density of the particle and density of the fluid. The fluid is water, so density and viscosity are one. So as you can imagine, and we said already, heavier particles are going to fall faster. And as you can see, most of these are darker here at the bottom and lighter at the top. And this is where we want to look for clays. So one thing that I want to stress, what settles down are heavier minerals, more crystalline phases generally, and things that we're not necessarily interested in. We want to look for clay fraction, less than 2 micron fraction, that is generally contained in the top part of the settling tube. So for example, in a water column, a 20 micron particle settles in about 2.5 minutes, whereas a 2 micron particles take up to close to 4 hours to settle. This has been calculated based on a settling distance of 5 centimeters and a mineral density of 2.6 grams per centimeter cube. So that means that after 3 hours and I think 50 minutes, you can take a pipette and take the top 5 centimeters from here, and that should contain your clay fraction. So once we have the clay fraction, we're going to move on to second stage of sample preparation and then sample analysis. So we know that there are many difficulties here. So what we want to do is, if we're looking at pure clays, we just want to look at different clays that are present. We want to look at oriented and random samples. So random clay powders require a larger sample quantity, and oriented samples can be achieved fairly easily. You will take less than 2 micron fraction with a pipette, for example, and then just, pipette it on zero background sample holder or a glass slide, and you leave it to dry. You can repeat that, so you will just get more layers, more samples, but what that means is that you're going to have clays that are going to just orient themselves that are going to lay down flat on the basal plane, and we're going to be able to see their basal plane reflections. So we have pre-treatment like carbonates or organic matter removal, for example. Now that we have, and then we've created our slides or samples, oriented samples, and now what are some things that we can do? We can saturate these samples with ethylene glycol or some other polar organic molecule that will help us test if there are some expandable clay layers present. And we'll see a shift in the basal peak, which I'm going to show later, if there are. Other procedures involve cation saturation. This involves interlayer cations. This is different from cation exchange capacity. And we can use sodium or calcium, for example, that will give us some nuances and peak shapes and positions. And then what is also common is heating clays and analyzing clays at room temperature, 300 and 500 degrees. Now that was oriented. Now, if we look at a process for preparing a random clay sample, these are much more challenging because clays just want to orient, want to have preferred orientation. They have preferred orientation. Like if you imagine yourself throwing a stack of papers, they're all going to lay down flat on the long side, on the flat side. So it's the same thing with clay. So now we have to agitate the sample, and we have to do some things to avoid this preferred orientation. Now, randomly prepared samples will show all HKL reflections of clay, and we can distinguish different polytypes like that, for example. So one of the ways of randomizing the sample is when you prepare it, there's like you can shake it in sieve it and then maybe side load it. That means that you will help these particles like fall down in different orientation, and you'll side load it against an etched or frosted slide that will have that won't have a smooth surface. It will have rough surface. So that's something that can be done. Another option is spray drying that offers a really good randomization. For that, you prefer to have a lot of sample, and it is a very useful method as well. So now if we want to prepare a sample for quantification, that is, again, a sample that should be random completely, not just clays. Everything should be randomized in the sample, and we should have a representative sample that will show us all the phases, all the mineral phases that are present. And what we want to do is try and follow sort of similar methodologies for clay preparation to achieve this. If the quantification is done using, for example, retool refinement, we can apply corrections for preferred orientations of clay to help us in our quantification. Another thing that is very useful is an addition of an internal standard. This improves accuracy very much. We need to homogenize the sample. This is something that is very important. We want to reduce the coarse grain minerals, and we also want to preserve the crystal structure. We don't want to damage the minerals. So we want to, and especially clays. So we want to, wet grinding is something that is very good in this case. Wet grinding minimizes the damage to mineral grains, and we normally use micronizing mill. So for this, again, you need to have a significant amount of sample. And this is done in grinding fluid like methanol. That's very useful because it evaporates very quickly, but it can be water as well. So for example, if you use 3 grams of sample, you can micronize that for 5 minutes to homogenize the mineral grains. Common internal standard, zinc oxide is used because it does not overlap with any of the major peaks in sedimentary samples usually, or soil samples. So when you're choosing your internal standard, you want to make sure that the internal standard will not overlap with peaks in your sample. And then you want this to be reproducible. So whenever you do this preparation, you want to make sure that you're following the exact steps, and you want to use the same amount of sample each time. All right. So now that we're done all that, we're moving on to the analysis. We're going to talk about X-ray diffraction. X-ray diffraction is a major tool for phase identification, especially for when analyzing clay-rich rocks or soil samples. It's the most widely used method for clay mineral determination. We get information for millions and millions of clay particles. And what we want to pay attention to is how we want to analyze. We already went through very careful sample preparation. So now we want to see how we're going to analyze our sample. It is very important to have good counting statistics. As we know, clay minerals have very broad peaks. They have low intensity peaks. And we want to make sure that the background noise is not going to hide these peaks. So we want to make sure that we have a high signal to noise ratio, and maybe test your instrument, run several scans, see what is the best. And if you have time, depending on where you work, you want to significantly increase the count time, so you would get larger and more defined peaks. So, okay, once we do that, we have our raw data, we have our diffractogram. So we want to figure out what that is. So we want to know, is this single phase sample or a multi-phase sample? How many, or do we have impurities, or how many impurities are there? Is there a lot of them, or just, 1 or 2 tiny peaks? And then also, what are we looking at? Is this sample random? Is it oriented? So then we're going to move on to phase identification, which involves using a database of standard diffraction patterns that we want to compare our sample to. So we're going to talk about, again, PDF 5+. We have PDF 5+ clay subfile that will that helps us in clay phase ID. And what we want to do, if we have more than one phase or not just clays, this is a general rule of thumb. You want to start with the most prominent phase. That doesn't mean the tallest peak. So you may see like a sharp peak, a well-defined peak that may throw you off, especially, for example, if you're synthesizing something and there is some, solvent left or something like that. So you'll get these like broad peaks, or you're doing like clay nanomaterials and you have these broad clay peaks, and all of a sudden you have like one sharp peak. So that may be deceiving. You got to keep that in mind. If we define what our most prominent phase is, which in natural samples is most likely going to be quartz, we want to mark that one and then eliminate it from the further search, and then we can search for lower intensity phases. Again, we talked about this already, but again, I want to stress the importance of having raw data in the PDF5+ database for clay analysis, because if you have a clay sample that contains broad peak or is interlayered, or clays that can swell and shift, you want to have raw data to compare that to, because just looking at at peak positions is not really going to tell you as much as having raw data to compare your sample with. We've seen this before. This is the PDF 5+ interface. We have a clay subfile. Within the mineral subfile, we have an option to select that we want to look at samples that only have raw data. And as you can see, we can compare this to our samples. I've shown this before. You can import your raw data and overlay it with this one. And you can also overlay several raw data diffraction patterns within the database and compare them. This is showing that right now we have 97 raw data patterns in the database, and I can tell you that the new edition is going to have another 50, more than 50 raw data clay patterns included. So this is an ongoing process, and we're gonna keep expanding the clay subfile. So now we just jump to Bragg's law, which I'm sure that everyone knows, but I just want to point out here one thing that's very important when you're thinking of clays and looking at clay diffraction patterns, and that is that D, or interlayer spacing, and 2 theta are inversely related. So if you have a larger D spacing, a larger interlayer spacing, that will correspond to the lower 2 theta value. So as we increase the D spacing, the 2 theta value will decrease. So that's something to keep in mind. So here we are. Sorry, don't mean to test you if you're hungry, but this was a good example. So we can take a look at these 2 sandwiches and understand how the inner layer changes, expands, and contracts. So we see 2 ham sandwiches, both have 2 slices of bread, ham, cheese, and tomatoes, right? So now this is a simple ham and cheese sandwich that we can take a look and say, okay, so this is our D spacing. These are our clay layers. These are our interlayered cations, and this is our D spacing. So now if we take a look at this sandwich, someone wanted a lot more toppings. So now we have ham, cheese, tomato, pickles, arugula, and this D spacing is a lot bigger than this one, right? So how the expansion and contraction works. If you take the sandwich to someone and they go like, hey, well, I mean, I don't like pickles and I don't like tomatoes, and they take out pickles and then they take out the tomatoes, this is going to be smaller, right? So this D spacing is going to contract. So this is the same thing that happens with clays, just not with pickles and tomatoes. And this is how that looks on the diffraction pattern. We've seen this before, but now I'm pointing this out again. We have montmorillonite clay that swells, a very highly expandable clay, and we're seeing a green diffraction pattern of an oriented, air-dried montmorillonite, and the D-spacing is 14.8 angstroms. After this clay had been glycolated, the interlayer spacing increases to almost 17 angstroms. So it increases a lot, about two angstrom. And what I pointed out, the larger the D spacing, the smaller 2 theta. So once we increase our D spacings, we will see a shift towards lower 2 theta. This is what we observed this on basal reflections. Here are other basal reflections where you can see an even more significant shift in the case of this montmorillonite. If you're looking at natural clay samples, these are sometimes going to be hard to spot in the diffraction pattern, so we mostly rely on the first peak here. What this looks like in the case of an interlayered clay, this is an illite smectite interlayered clay, air dried. We talked about this, I think, in the first talk. Air dried interlayer clay, even though it's interlayered, it acts as a coherent scattering unit, and it shows this one peak that contains both illite and smectite. And then once we glycolate it, illite is non-expandable. So this is going to be the illite peak, and smectite peak will shift towards the smaller 2 theta angle. All right, so now we know all that. We still need to figure out how to interpret our diffractograms. And if we have natural samples, the best, maybe, well, I guess the best way is to keep in mind what are the common minerals that clays are associated with. And I mentioned before, but the more you know about your sample, the easier this gets, or more straightforward. So you can think of, okay, so I'm most likely going to see quartz. I'm probably going to see some feldspars. I may see chlorites, mica, calcite, dolomite, and iron-bearing minerals, among others. But these are some that we can start with. And then clays. So let's look at some common clays. Kaolinite, illite, montmorillonite, vermiculite, chlorite. These are the interlayer spacings. So kaolinite has a spacing of about 7. The spacing, the kaolinite is fairly fixed. So you can kind of rely on this being 7 angstrom. Illite, again, non-expandable, 10 angstrom D spacing. Smectite's variable D spacing. Vermiculite, also variable. And then chlorites are not variable. They're fairly fixed, and they're around 14. So as you can see, these can overlay, and we can often confuse one for another. And I want to mention that mica, muscovite, has the same D spacing as illite, around 10. So now, what our samples look like? Our samples are not very helpful, and like we can take our sample and take a look at it and say, okay, so I have these minerals in here, because they're generally just brown. So whether it's a black shale sample or some their sedimentary sample or soil sample, they're mostly brown, so not very helpful. So we want to try and, this is a soil sample, we want to ground it as much as we can. We don't want to shear the grains. We want to pay attention to how we're doing this and sieve it. So now I have 2 soil samples that I want to show you how I work through them. So soil sample 1, we have 5. I've decided to have 5 minerals: quartz, orthoclase, a feldspar, muscovite, illite smectite mixture, and kaolinite. And then the second clay sample: quartz, illite smectite mixture, kaolinite, albite, which is a feldspar, and in this case, chlorite. Here we did not have chlorite. So let me show you how some of the steps of how you can do that. So I'm showing you this in PDF 5 plus. Whatever software you use is going to be similar you're going to have similar filters, and I want to show you some of the steps that are very useful here. So in my case, I'm going to use Civ Plus. I'm going to import my diffraction pattern. So Civ requires you to prepare your pattern to make sure that everything is correct for the analysis. I've done this before. So I'm just going to import all of these peaks. So I'm going to reset filters here. And this is something that will happen with everyone. If I say like no filters or anything, don't apply filter. And we're going to wait and see what happens. So as you can imagine, the tallest peak is quartz. So that is not going to be a problem to be identified at all. So I'm going to go here and say accept phase. And then let's see what my next option is. So now I'm getting many things: iodine, helium, so things that are not necessarily present in our samples. And we know that we have a lot of stuff here that we don't necessarily see because the quartz peaks are so tall. So what we want to do, we want to make sure that we don't have too many filters and too many things that are looking for a very accurate determination, which these are super useful when you have something that's synthesized in the lab. You know what you're looking at, something that are very highly crystalline, super useful. As I'm, getting rid of the filters, I'm getting more and more things here. So I'm just going to jump here to albite because I know that that is in my sample. And I'm going to say accept phase. A quick note here. Sometimes you will have like a bunch of peaks here, and you know that you have some feldspars. You know that you must have some feldspars, but you can't figure out which ones you have. So then you go back to your search and your filters, and you force, you say, I want to look for feldspars. If you want to do that in the PDF 5+ in Civ, that option is going to be in your search history. So you want to search for feldspars in your actual search. You can go to, for example, classifications and look for feldspars here. Or you can go by mineral name. So I can go feldspar family. I'll say search. It will perform this search. Now I can close this and go back to Civ and go to filter. And then I'm going to go to search history instead of searching ICDD filters. And I'm going to say feldspar family. And if I apply this filter, I'm going to get feldspars, which I already chose one, so I'm not going to do right now. I'm going to go back to ICDD filters and say, I want to look at only minerals. So I'm going to go to mineral related. This will involve all minerals plus clay. So let's see what we're going to get here. So I'm getting this muscovite and chlorite, and now your search continues. You can go and say, let me look at only clay. And now I'm getting chlorite. So I have this peak here, and I am pretty sure that I have some kind of chlorite. So let's go with this one. But this is something that you're going to have to figure out in your sample. So now when you're looking at the position, you take a look and be like, oh, what's the latest thing that I'm looking at? So now I'm looking at this bluish line. So I know that this is covering the peak. So I'm going to say, yes, accept phase. I want to say elite smectite because I want to test for smectites. And now it's showing me again these peaks here, but now I want to go and look for maybe kaolinite. So here it is. And I'm going to say, okay, so accept phase. And this is going to be my more or less phase ID. So another thing for you to keep in mind, if you have a clay peak that's very wide and very broad, and then the peaks, you're either going to have sticks or peaks like this, they will always be wider than your peaks. So in this case, you can, change the peak shape and try and model your X-ray diffraction pattern. And you always want to take a look and make sure that what you've done makes sense, even though it may look chaotic. You want to try and make sense of it and make sure that you know what you're selecting and that you're fairly certain in your choices. And then you can move on to another type of analysis, like maybe whole pattern analysis or something similar. So back to our presentation. So as we said, we have soil sample 1, soil sample 2. Not surprising, they're really similar, both from an area close to where we work here in Pennsylvania. So you expect to have similar soil composition. So now what do we want to know? We want to know which clays we have in this soil. And we, for that, want to look at oriented slides, and we want to look at clay fraction. So this here is clay fraction, soil sample 1. It's been oriented. We put some suspension, some drops on the zero background sample holder and dried it. So what do we see here? We see 3 clay peaks, and what do we see? 14, 9.9, or let's say 10 and 7. So we have our major clay peaks. 14, is it a chlorite, or is it a smectite? Or it's 7, we can assume that it is kaolinite, and this 9 is illite. So now we want to, if we take a look at our other sample, we get the same thing, 14, 10, 7. So we want to figure out what these peaks represent, which clays these peaks represent. And then we've also glycolated these clays. I'm going to show just one here because they're the same. I was hoping very much to show you a peak separation, but unfortunately there are no expandable clays here. How do you know? There's no change in peak positions and the values. As you can see, these are the same, 14 and 14, 10, 10, 7, we can't see the one, but it's also 7. So nothing has changed. There is no shift. And we can conclude that there are no expandable clays. The reason why I wanted to show you on the existence of expandable clays so much is because you shouldn't expect anything to look as nice as the examples that I've shown you, because it is very hard to achieve that level of accuracy. So in your case, this would look pretty messy. You know, if this was an interlayered peak, this peak would sort of become like a hump. It would push a little bit or move a little bit towards lower 2 theta. And that's something for you to keep in mind, that, you know, you need to have a database and you need to have examples that you can compare your data to, but you got to keep in mind, which I'm sure that you know, is that data is messy. Okay, so this brings us to the end, and I just I'm gonna leave this here with you. You can go back and take a look at the presentation if you want, or just go back to the end of the presentation and grab this. These are very useful references, and out of these 3 references, you can most likely get most things that you need about sample preparation and identification. Thank you.
Visit ICDD.com to register for upcoming webinars and to watch previous ones.